Recurrent neural networks are made up of recurrent neurons, which are different from the regular neurons that we've seen so far, because these recurrent neurons have memory or state. Why do we say that? What does it mean when we say this? In order to understand recurrent neural networks and how they work, we have to go back to the basic building block, the recurrent neuron. The simplest of all feed-forward neural networks is one which comprises of a single neuron. This is the neural network that we used for linear regression. This is the basic structure of the simplest feed-forward neuron. We have the X variables, that is the features, feed into this neuron, and we get a corresponding output, that is the Y variable. A recurrent neuron is aware of time instances. At any time instant t, the features or the x variables that are fed into this neuron are represented by x subscript t, and the corresponding output is y subscript t. The recurrent neuron takes its output at any time instant and feeds it back as its input in the next time instant. That means y of t minus 1 is the input to the recurrent neuron at time instance t. And this simple tweak of a feed forward neuron is what makes a recurrent neuron. And this simple tweak is what gives the recurrent neuron the ability to learn from the past. Now, let's look at all the labels that we've seen in this recurrent neuron. Y of t is the output at time instance t. The value of y at time instance t depends on two bits of information. It depends on y of t minus 1, which was the output of the same neuron at time t minus 1. In addition, y of t depends on x of t. These are new inputs to the recurrent neuron, which are only available at time t. They were not available earlier. And these recurrent neurons laid out over time is how you build a recurrent neural networks. Just go in and substitute different values of t. Let's say t runs from 0 through 10, and then lay out the resultant neural network on a time axis. So if you have 10 time instances within your data set, your recurrent neural network will have 10 layers. This process of laying out a recurrent neuron on a time axis is called unrolling through time. Unrolling through time is how you create layers in a recurrent neural network. Here we have a single recurrent neuron unrolled through time. Notice the inputs at every time instance. They range from x0, which is available at time instance 0, and go up to x3, available at time instance 3. This is the same recurrent neuron represented at different instances in time, which is why the output of the neuron y0 is fed back as an input to the neuron at y1. The time axis at the bottom shows the passage of time and makes it clear that this is one neuron unrolled through time. Here we shown the single neuron, and the output of the neuron is fed back to its input. A better representation would be that the output at y0 is fed to the neuron at time t1, output at y1 is fed to the neuron at time t2, and the output y2 is fed to the neuron at time t3. Let's see what are some of the basic characteristics of a recurrent neuron. It'll be much clearer if we compare and contrast it with a regular neuron. In a regular neuron, the input to the neuron is a feature vector x1 through xn. The output is a scalar. For example, in a linear neuron, the output y is equal to wx plus b. We may have an additional activation function as well. In a recurrent neuron, the input is a feature vector, exactly the same as in the case of a regular neuron. The output of a recurrent neuron is a vector as well. The input to a recurrent neuron will range from x0 to xt, where t represents instances in time, and the output will be y0 to yt, an output for every instance in time. Recurrent neurons accept as its input the previous output of that same neuron. This has very great significance because recurrent neurons remember the past, they possess memory. Feeding back the output into the input allow the recurrent neuron to learn from the past. This stored state could be more complex than simply y of t minus 1. All we've seen so far is the previous output fed back to the input. This stored state, however, can be made more complex by structuring the recurrent neuron in a slightly different way. We'll see that later on in this course when we talk about long short term memory cells. The internal state within a recurrent neuron is represented by h of t. This is to distinguish between the internal state and the output of the neuron in the previous time instance, which is y of t minus 1. As opposed to a regular neuron, a recurrent neuron has two weight vectors, W of x. This is the weight vector that corresponds to the inputs that are present at that instance in time, and W of y, which is the weight vector that corresponds to the output at the previous instance in time, which is fed back to the input of the recurrent neuron. You can see this visually here. W of x is used to weigh the current input, that is x of t, and W of y is used to weigh the previous output, y of t minus 1. And here is the formula which represents the output of a recurrent neuron. W of x into x of t plus W of y into y of t minus 1 plus b. The bias is obviously added just like in the case of regular neurons, and phi is the activation function. Again, the same as in the case of regular neurons. A recurrent neuron at any time instance takes in two bits of input, the input x that is available at that time instant, and the input y of t minus 1, which was the output of the same recurrent neuron at the previous time instance. This feeding back of the output at the previous time instance back into the recurrent neuron allows it to learn from the past. This is the memory or state that a recurrent neuron holds.